If you can master this IC, it can really save you in a lot of projects. This IC offers capabilities that significantly increase the quality of your project. In this video, I want to talk about this IC and teach you how it works and how to get it up and running. Throughout this video, you will also see some of the applications of this IC so you can use it in similar situations in your own projects. In addition, in this video, I'll talk about different types of 7-segment displays and the correct way to power them up and use them in your projects. Stick with me for a few minutes and you will gain incredibly useful skill forever. Hi everybody, this is Electronic Wizard at your service. When we are using a microcontroller in a project, it often happens that we need more input-output pins, right? It doesn't matter what kind of the microcontroller it is, AVR, STM32 or other types. A lot of times we just run out of pins. Or sometimes we might need to convert serial data into parallel. I think it's better if I give you an example. If we want to display 2-digit numbers, we need to use at least 2 7-segment displays. This means we have to dedicate 40 pins from our microcontroller just for displaying 2 digits. If the microcontroller we are using has a limited number of pins, we might run out of I/O pins for other tasks on the microcontroller and run into problems. This is exactly where the 74HC595 IC or similar ICs come to rescue us. What is the 74HC595 IC? Is it a 7-segment display driver? Of course not. Even though we can use this IC to drive a 7-segment display, it is not primarily or originally a 7-segment display driver. Actually, it is a shift register. What is a shift register, you may ask? I'll explain. A shift register is basically a small memory where we can directly access its values on its pins. For example, if we want to compare it to other types of memory like RAM, we first have to give the IC the desired address and then the IC would give us the data stored at that address. But a small memory like this shift register can directly put the data stored in the IC's internal memory onto its pins. Another property of a shift register besides being a memory is that the values of the bits stored in its memory can shift between memory units by applying a clock pulse to the CLK pin. For instance, if we apply one clock pulse to the CLK pin, the bit stored in the memory unit number 7 moves to the memory unit number 6. The bit stored in the memory unit number 6 moves to the memory unit number 5. The bits stored in the memory unit number 5 moves to the memory unit number 4 and so on until the bit stored in the memory unit number 0 exits from the IC. Look, we had these values inside the shift register before a clock pulse and we got these after the clock pulse. If you look closely, you can see that the bits are shifted to the right. These two properties I mentioned about the shift register IC allows us to use it in really cool applications. So far, I have talked about the shift register ICs in general, and what I have said applies to all shift register ICs, right? Now, it is time to talk specifically about the 74HC595 IC so we can get more familiar with it and better understand its applications. This is the pinout diagram for the 74HC595 IC that you are seeing. Pin number 16 is used for connecting the power supply, which can be anywhere between 2 volts and 6 volts. This means that both 5 volts and 3.3 volt microcontrollers can directly connect to this IC. Pin number 8 is used for connecting to ground or 0 volts. This IC actually has 8 1-bit memory units inside, and pins number 15, 1, 2, 3, 4, 5, 6, and 7 are the outputs of these memory units. Pin number 9 here is also used as a serial output. For example, when we want to connect several of these ICs together, pin number 9 as the output of the IC connects to the pin number 14 of the next IC. 9 to 14, 9 to 14, 9 to 14. All right. I didn't mention that pin number 14 here, I mean SER pin, is the input for the IC. Pin number 13, output enable pin, is used to enable the outputs. This means that if we enable pin number 13, the output pins, I mean 15, 1, 2, 3, 4, 5, 6, and 7 will have values, and otherwise they will be disabled. That is, they will be high impedance. This feature can be super useful. I'll definitely give you an example of this later in this video so you can see how useful pin 13, also known as OE, can be. Pin number 10 is used as a master reset to clear all the data inside the IC's memory units. Pin number 11 is used for shifting the bits, and pin number 12 is used for transferring data from the memory to the outputs. This pin number 12 also does something really useful. I'll give you an example later so you can get more familiar with it. So far, we have covered the general overview of the IC and its pins. Now, we need to understand how the IC actually works. To do this, I need to give you a numerical example so you can fully grasp the concept. Let's say we want to show the digit 4 on the display. For this, we need to create this specific bit pattern on the display pins. I'll explain more about 7-segment displays later, but for now, let's just assume we want to send this specific bit pattern to the display, meaning we need to have the value 011001110 on the output of this IC. Now, what process do we need to follow for this? First, we need to place a 0 at the input, which is pin number 14, and then give a clock pulse to pin number 11 so that the 0 enters memory unit number 7. After that, we put a 1 at the input and again give a clock pulse to pin number 11. By doing this, the 0 that was previously in unit 7 moves into memory unit number 6, and the input value, which is 1, is stored in memory unit number 7. These values are not yet on the output, they are only written inside the memory. Next, we need to place a 1 at the input and again give a clock pulse to the pin number 11. With this, the 0 that was in the memory unit number 6 moves into memory unit number 5. The 1 that was in the memory unit number 7 moves into memory unit number 6. And the 1 that was at the input is stored in the memory unit number 7. We continue this process until the last bit, so after 8 steps, the values we wanted are stored in the memory. Now, to transfer these stored values from the memory to the output and form the voltages on pins QA through QH, we need to apply a clock pulse to pin number 12. By applying a clock pulse to pin number 12, the values written in the memory is transferred to the output. In this point, you may ask what I mean by a clock pulse. That's a good question. When I say apply a clock pulse to pin number 11 or 12 or any other pin, what I mean is to momentarily change the voltage of the pin to high, then bring it back to low. For example, pin number 11 from 0 volts to 5 volts, then bring it back from 5 volts to 0 volts. The same goes for any other pin like pin 12. You momentarily make the pin voltage high, then bring it back to low. That's simple. Up to this point, we have learned the process of loading values into the 74HC595 shift register and how it works. Now is the time to see some applications of this IC so we can really understand how it can be used in practice. One of the applications we can use the 74HC595 IC for is to drive one or more 7-segment displays. A 7-segment display is a type of display made up of several LEDs. By turning these LEDs on and off in a specific pattern, we can display numbers or even some letters on these displays. For example, to display digit 1 like this, we need to turn on LEDs B and C and turn other LEDs off. To display digit 6 like like this, we need to turn on LEDs A, C, D, E, F, G and turn LED B off. There are different ways to create our desired pattern and consequently our desired digit on a 7-segment display. The simplest method is to connect all the LEDs directly to the microcontroller pins and create the desired pattern by setting the pins high or low. This is the simplest way. However, this method has many drawbacks. First, the LEDs have to draw current from the microcontroller pins to light up. Essentially, the microcontroller has to supply the power consumption of the LEDs itself. Second, this method occupies the microcontroller pins, which are very limited in numbers. If you only want to use one 7-segment display in your project, it might not be a huge problem. But what if you want a lot of 7-segment displays, say 20 displays in your project? Can you still use the microcontroller pins then? Absolutely not. So there must be a method that allows you to drive a large number of 7-segment displays using fewer microcontroller pins. One of the common methods is multiplexing. This means you display only one digit at a time, but by switching between digits on the display at high speed, you create illusion of continuous number on the display. For example, let's say we have 4-digit display and we want to show the number 9, 5, 7, 8 on them. First, we need to display the digit number 9 on the display number 4, then turn off the display number 4. After that, we display the digit 5 on display number 3, then turn it off. Then we display the digit number 7 on display number 2 and turn it off. And finally display digit 8 on display number 1 and turn it off. And then we repeat the whole process again, showing number 9 on display 4 and 5 on display 3 and so on. If we do this at high speed, the human eye won't be able to detect the LEDs turning on and off, and it will create the illusion of constantly displayed 4-digit number. The method I just explained is multiplex 7-segment display driving, which reduces the number of pins needed to drive the display. For example, to directly drive 4 digits, you would need at least 7 times 4 pins. Since each digit has 7 LEDs and 4 digits are used, you would need at least 28 pins to connect a 4-digit display directly to a microcontroller. You may ask, why do I say at least? Great question. Because many 7-segment displays also have a decimal point, which is actually the 8th segment used for displaying decimal numbers. For example, if we want to display a decimal number like 32.59, for example, we need to control this 8th segment, the decimal point. In that case, each digit would have 8 segments, and in total we would have 32 segments. In multiplex mode, we need one control wire for each segment, these wires here, and a separate wire to enable or disable each digit, these here. So by considering another segment for each digit for that point, this segment here, for a 4-digit display like this one, you need to connect at least 12 pins to the microcontroller, just like this module which has 12 pins. Look, it has 12 pins. A multiplex 4-digit display works like this. You place your desired digit pattern on the pins A through G using microcontroller, and then by enabling each of these pins here, for enabling each digit, you can activate the desired digit and display the pattern formed on pins A through G on that specific digit. For example, if we enable DE1, the pattern formed on pins A through G will be displayed on the first digit. If we enable DE2, it will be displayed on digit number 2, and if we enable DE3, it will be displayed on the third digit, and by enabling DE4, it will be displayed on the digit number 4. If we enable several DE pins simultaneously, our desired pattern will be displayed on all of them. For instance, if we enable DE2 and DE4 at once, the pattern present on pins A through G will be displayed on both digit number 2 and digit number 4 at the same time. The multiplexing method is good, but
that it also has many drawbacks. The main problem with that method is that it still occupies a lot of pins. I mean, we need 8 pins for the pattern and at least 1 pin for each digit to enable the digit. For example, if we want to have 27 segment displays, we would have to dedicate at least 28 pins of the microcontroller just to drive the display, 8 pins for formatting the pattern, and 20 pins for enabling each of the 20 digits. Another problem is that the LEDs are still connected directly to the microcontroller pins, and the power needed to light up the LEDs must be supplied by the microcontroller. Furthermore, the microcontroller has to dedicate a large part of its processing power for changing the pattern from one digit to another. Another drawback is that while the multiplexing method creates a visual illusion for human eye, making them see the digits as constant on the display, the digits created with the multiplexing method reveal their flaws during video recording and photography. When filming, this updating of the segments is clearly visible. These drawbacks led me not to use the multiplexing method in the 10-channel lighting system project, and instead I used a different method that doesn't have these issues. Oh, by the way, I forgot to mention that this video you are watching right now is part 4 of the 10-channel lighting system project with an infrared remote controller, which we did it using an STM32 microcontroller. In that project, we used 4 74HC595 ICs, 2 for 7-segment displays, and other 2 for driving the channels. Anyway, let's move on. Now it's better to go and see how to use the 74HC595 IC for driving a 7-segment display and examine its advantages together.
This is how we use the 74HC595 IC to drive a 7-segment display. All we need to do is to connect pins 11, 12, and 14 to the microcontroller, and that's it. After that, we can use just these 3 pins to create the 8-bit we need to form the pattern on the display pins. And it is not just that. We can connect an infinite number of these ICs together in serial, and as a result display and control an infinite number of digits using only these 3 pins from the microcontroller. On the other hand, since these pins are signals and are not directly connected to the LEDs, they don't draw any current, and the microcontroller doesn't need to supply the power required for lighting up these LEDs inside 7-segment displays. In fact, the power needed to light up these LEDs is supplied by the 74HC595 IC itself. And finally, since these ICs have their own memory, the microcontroller only generates signals on these 3 control pins when it needs to change the displayed value. And when there is no need to change the displayed value, the microcontroller doesn't spend any processing power on displaying the digits. So with this method, the microcontroller can easily focus on its other tasks. This also ensures that there is no flickering on the display during video recording, and the digits are displayed very smoothly and cleanly. We have pretty much covered everything up to this point, and only a few minor details remain that I need to mention. If I explain these few points as well, we can wrap this up. The first point is that we can use the OE pin to prevent anything from being displayed on the screen when we first power up the circuit. This means we can pull the OE pin up to 5 volts so that the output is disabled at the start of the circuit. If you look closely, there is a line over the name of this pin, which means that this pin is active low. It means that it activates with 0 volts and deactivates with 5 volts. So by pulling up this pin to 5 volts, we deactivate the pin, and then we can activate it using the MCU pin by connecting this pin directly to the one of MCU pins. We do this because when the IC is powered up, the values stored in its memory units might be random zeros and ones at the very beginning, and this can cause an undefined pattern to be displayed on the 7-segment display at the startup for a moment, which doesn't look good and makes the project seem unprofessional.
In the first version of the 10-channel lighting system project, I didn't do this and it caused an undefined pattern to be shown at device startup. I really didn't like that situation at all. On top of that, since I used the same IC to determine the status of the channels, at device startup some channels would randomly turn on and some other channels would randomly turn off until the microcontroller put the appropriate value on the IC. This was even worse than showing an inappropriate pattern on the 7-segment display.
The next point is pin 12, which is used to transfer data from the memory to the output. If this pin didn't exist, when the microcontroller was changing the value, we would temporarily see undefined values and unpredictable patterns on the 7-segment display, and that is not nice at all. But this pin allows the microcontroller to firstly apply all its desired changes to the IC's memory, and then with a single clock to pin 12, transfer the changed value to the output. With this, there will be no more undefined and ugly patterns on the output. The reason for having this copy of QH here as an output is also the same. If this pin didn't exist, the shift operation wouldn't happen because the value of the main QH pin here only changes when pin 12 is clocked, and it practically can't shift data to the next IC.
Besides all of these, I also want to point out a few other electrical tips regarding these circuits that are good to know.
Sometimes the 7-segment display we are using might operate at different voltage compared to the IC's operating voltage. For example, the 74HC595 IC works with voltages between 2 and 6 volts, but our 7-segment display might work with 12 volts, for example, or the LEDs on the display might have higher power and require a lot of current to light up, which the IC's pins might not be able to supply that amount of current. In this case, we need to use a transistor circuit to switch the voltages to the 7-segment pins on and off. Another important point is that to limit the current for the LEDs, we should place resistors on the pattern-related pins, I mean pins A through G, and we should avoid placing current-limiting resistors on the common pin, I mean CE or DE pin here, so that the light of all LEDs in the display is completely uniform, smooth, and clean.
Alright my friend, with a little practice, you can master this IC and use it in your project. By learning this IC, you will also become proficient in important parts of the 10-channel lighting system project. It is really good, cool, and versatile IC. Anyway, thanks for watching me. Thank you for sticking with me until this point in this video. If you like this video, please give it a thumbs up, and if you are interested in electronics and microcontrollers, subscribe to my channel. Until the next video, take care of yourself and have a good one. See you in the next video.